So, see, you have one problem example, air enter at diffuser. That's that. Okay. The temperature is 30 degrees C. So if you look at the table, it didn't read the book. If you see the book, you will get the R is 0.287. Okay, now the important thing, you see this? Okay, I do that, but in my calculator, it will be giving me 1.4 times 287 times 300 Kelvin. Because of this small, yes, K mean kilo. 1000. Okay, so this one will be 287 joule kilogram per Kelvin. And then you see the air temperature is 30 degrees C, but you need to convert it into Kelvin. Yes. If you are not doing that, you will get different result. If you get different result, your Mach number will be. Okay, any question? Okay, now you know that compressible flow is very complicated, but of course in the class we need to simplify our problem. Okay, in most of the devices such as nozzle, diffuser, or turbine blade, the flow quantities only vary on the one direction. Okay, from the inlet to outlet. It does not. In reality, it is vary from this point to that point, right? From the core to the blade, it will be different. But the most likely different is from the inlet to the outlet. Okay, so if you look at the inlet and outlet, you see only one line, which means it is a one-dimensional problem. Okay, so most of the time we will deal only with one-dimensional. Most importantly, isentropic flow. Why isentropic flow is important? Because if you are not having those isentropic flow, your stagnation properties will change. Okay? If your stagnation properties change, you cannot analyze it anymore easily. I mean, you can still analyze it, but it will be more complex. Okay? So, if you have this thing, right? If you have this thing, you have isentropic flow, then T naught over here will be equal to T naught over there, will be equal to T naught over there. T naught over here will be equal to T naught over there, will be equal to T naught over there. However, T over here is not the same with T over there, is not the same with T over there. The static properties is not the same, only the stagnation properties. So if you have P over here, it will not be the same with the P over there, it will not be the same with the P over there. Okay, so let's put this one inlet, this one throat, this one exit, inlet, throat, exit. So you see, this one is not the same, but this one is the same. Okay, that's why we have to have those isentropic flow. And also, if your isentropic flow is not valid, you cannot get this one anymore. Okay, this correlation only for isentropic flow. Other than that, you cannot use it. Okay, so every time you are working with the compressible flow, you need to take an assumption that the flow is isentropic. If the flow is not isentropic, you cannot have it. Okay, let's take a look at this one easily. Right? You have a flow of carbon dioxide inside a nozzle, right? The stagnation properties at the inlet, okay? At the inlet is 1400 kilopascal and 200 degrees C. Why we call it the stagnation properties? Because it has a very low velocity. Right? You remember, if you have a low velocity, what will happen to your T naught? T T naught is equal to T plus P square over 2 Cp. In this case, since this one is very low, so this one will be negligible. Okay, if this one is negligible, so you got your T naught is equal to only for a very specific case when the inlet velocity is low. Okay, if your T naught is equal to T naught equal to T, 1, right? 1 to the power of whatsoever, still 1. Even you power it to 0, it's still 1. 1 to the power of 0 is still 1. So then you get your P naught is equal to P, which means those condition is your isentropic properties. Now you need to find the condition when the pressure is decreasing by 200. So at the moment you have 1400, right? Now you need to get the condition when the pressure is decreasing into 1200. What will happen? When you decrease into 1200, you calculate it using this, right? So you will get your T. Because T naught is constant. Remember, T naught is constant, but T and P will change. Now the P is changing into 1200. So you can calculate your T at P equal to 1200. Okay? If you do that, okay, so this one is that because it is stagnation properties. So now we look into the first location where the pressure becomes 1200, right? Your P naught is equal to 1400 or 1400. That is your P naught. The top one is your P at that particular point. And then you get your T naught is your T inlet. So you get the T at those particular point is 457. Okay, yeah. So your P naught, which is equal to P inlet, is kilopascal, right? Then you have your T naught is Pi is how many Kelvin? 473. 473 Kelvin. Okay, so what I will do is I will just put this P equal to T, right? So 1400, 473. Okay. If it is now 1200, you get
457.
457. Okay. This one velocity is negligible, but here you can calculate the velocity, right? Because the velocity is, you calculate it from here. T naught is equal to T plus V square over 2 E. So if you know this one, you know this one, you know that one, you can calculate your V. So you get your velocity is 164.5, right? And then you calculate your rho. Your rho is P over RT, right? Your rho is equal to P over RT, so you will get your rho. Okay? Once you get your rho, you can calculate your mass flow rate. Right? Your mass flow rate, or you can calculate the area. Okay? The area at that particular position. Because mass flow rate has to be constant, doesn't matter. Right? M dot here is equal to M dot there. But area changing, density is changing. Because M dot is equal to rho A V. So rho you know from here, velocity you calculate from there. So now you can calculate your area. Okay, now you get your area. Same goes for 1000. You calculate that. 1000, then continue with 800, right? And then 600 and 400. Okay? If you do that, you will get this. If you do that, you will get this one. You see, the temperature keep decreasing as the pressure is increasing. Sorry, decreasing. Right? So it decreases. But then, the interesting part is here. The interesting part is the area. You see, the area is decreasing when you increase the velocity, right? But then, after some time, it's increasing again. And then you see the Mach number is keep increasing. So what is the consequence of it is that if you are in a subsonic flow, if you want to increase the velocity, you need to make the area smaller. That's what you usually do, right? When you want to water your plant and the plant is far away from you, what you will do is you squeeze it. When you squeeze it, you will get higher velocity. When you get the higher initial velocity, of course, by using parabolic profile, you will get higher or longer distance. Right? That's what you will do. But if you have gas, you do that, okay, after some time, the velocity will stop. Okay, and this condition is the so-called choke flow. Okay, one, right? So you cannot increase it again. That's it. Doesn't matter what. You just reach one number of 1 and that's it. You cannot increase anymore. So the only way to increase it further is by installing a diffuser. Right? Okay, so that's what we see. Okay, if you do not believe with this calculation, okay, and I hope you do not, do it on your own. Right? Okay, so this is what we have discussed, right? The pressure decrease, the temperature and speed decrease, while the velocity and Mach number increase. Right? So this is makes sense because of this. Okay.